Welcome you once again to the next lecture of satellite communication. So, learners, if you recall, in the previous lecture, we had taken an example, and in that example, we had to launch a satellite through different stages before putting the satellite into its orbit. So, the final orbit of the satellite is a GSO orbit, or which is, we can say, the orbit is an orbital height of 42,164 kilometers from the center of the Earth, keep it in mind. Okay. And if you see the picture, in this picture, first we have to launch the satellite from the surface of the Earth to an orbit, that is a parking orbit. In parking orbit, at this particular location, which is called the perigee, we have to give an additional thrust. By that, the velocity change happens and the orbit of the satellite changes from parking orbit to GTO orbit. That was the first stage of, or stage 1, when the satellite changes from parking orbit to GTO orbit. And further, at the location of apogee, particularly when the satellite is in GTO orbit, at the apogee point, we have to put additional thrust so that the orbit of the satellite will change from GTO orbit to GEO orbit. So that is the second stage of launching the satellite into GEO orbit, or that is also called GSO orbit. So let us revise what we have done in the previous class. So as I said, that first of all, we have to find when we are launching the satellite into parking orbit. So what is the velocity at which the satellite will rotate in the parking orbit, which is a circular orbit? So we have to find out this velocity by using the second law of, or it's not second, the third law of Kepler, assuming the orbit is a circular orbit. So that velocity we can represent as V. Further, when there is a change of stage, or when there is a change of orbit from parking orbit to GTO orbit, this particular point, which is called as the perigee, the perigee point is common for the elliptical orbit, which is GTO orbit, and the parking orbit. So when the satellite will move from parking orbit to GTO orbit, since this particular point, which is called as the perigee, is common point in between the parking orbit and GTO orbit, then we have to find out what is the incremental velocity, or what is the additional velocity we have to put such that there will be change of the orbit for the satellite. So with that velocity, we will calculate as a new velocity, that is called velocity at perigee. So which I can represent by a symbol Vp. So in order to change the orbit of the satellite, we have to find out for the elliptical orbit what should be the velocity. And we know by the second law of Kepler, when the satellite moves in an elliptical orbit, the velocity of the satellite does not remain constant throughout its orbital period around the Earth. Okay, so particularly when the satellite is close to apogee point, velocity will be very high, and when the satellite goes towards the perigee point, goes towards the apogee point, the velocity reduces. So throughout the orbital movement or rotation, in particularly for elliptical orbit, the velocity is different. However, for circular orbit, the satellite moves at a uniform velocity throughout the orbital period. Okay, so that is why we are calculating what is the velocity at perigee point, since the velocities are different in GTO orbit, which is an elliptical orbit. So we have to calculate what is the velocity at perigee. Okay, so because if we think that perigee is a point which is common in between parking orbit and GTO orbit, and if you assume that at this particular point the satellite will move same velocity. For example, if you see, this is the parking orbit and this dotted line represents the GTO orbit, and this point is common point in between parking orbit and GTO orbit. And if you assume that since this particular point is common in between parking orbit and GTO orbit, then hopefully the velocity must be same. Okay, that thing might came into your mind, but the answer is not exactly like that, because if you think in that way, then there will not be change of orbit. If the velocity of the satellite will remain same, then there will not be any change of orbit. So orbital change happens when the velocity change happens. Otherwise, there will not be any change of orbit. So we have to find out that what is the incremental velocity whenever the satellite changes from one orbit to another orbit. And this difference is called the additional velocity required to put the satellite into another orbit, that is called GTO orbit. Okay, so that we have done here. So when the satellite was moving in parking orbit, we can use the third law of Kepler for circular orbit. So we have calculated it is coming around this value. Similarly, for perigee, we have to calculate what is the velocity. So this formula we have used for, it is for the elliptical orbit. So here this R is this value. Okay, because R is the orbital height, so that orbital height is nothing but from this point to this point. That means it is calculated from the center of the Earth. And this A, okay, so this A represents the eccentricity. If you find out, you will get the value this much. Okay. So in this way, we can find what is the incremental velocity. It is coming somehow 2.3 kilometers per second. So if the velocity will be increased of this value, then there will be change of orbit. Okay. Now, what happens whenever the satellite changes from GTO orbit to GEO orbit? So we have to first of all find out what is the velocity at apogee. When the satellite moves in the GTO orbit, we have to find out what is the velocity at apogee. And when the satellite changes its orbit from GTO orbit to GEO orbit, then for GEO orbit, so GEO orbit, it is an circular orbit. So for circular orbit, what is the velocity of the satellite? So which we calculate as B. So this difference will give us what is the incremental velocity we require. So this is first part. Second part, what we are doing here, we are calculating what is the velocity at apogee. And we are calculating the velocity for GSO. Since the GSO orbit is a circular orbit, so you are using this formula. Okay. And here, since the velocity, here the orbit is an elliptical orbit, so we are using a different formula. All right. So these values are, and the A value, these are known. So here, yeah, I will ask here what the value of R you will consider. You have to take this value. That is, we are always calculate from the center of the earth. So it will be this value. So what this is, it is nothing but 42,164 kilometer. All right. So, and what is the value of A? A is the eccentricity, and how we can calculate eccentricity? You know this value. That means this point to this point, this distance, you know, which is nothing but this height. That means altitude is 560, it is given, and radius of the earth is 6378. So this is 560 plus 6378. So this much you got, and this much is 42,164. You just add these two values divided by 2, that will come as eccentricity. Okay. So here, if you observe that what is the incremental velocity we require it is 1.441 kilometer per second. So with that incremental velocity, there will be change of orbit from GTO orbit to GSO orbit. Understood? So now, let us have a look with some other parameters. So till now, what we have discussed, that we have launched a satellite, and the satellite is moving at some velocity. But when we're launching the satellite, then what is the angle of inclination? At what inclination angle we should launch the satellite? So that inclination angle depends upon what is the latitudes from which we are launching the satellite. What is the latitude of that point, latitude of the launching site? For example, we are launching our satellite from Sriharikota. So what is the latitude of Sriharikota? And what is the azimuth angle and orbit inclination? Okay, so the orbit inclination is related to these two parameters. One is called the azimuth angle, another parameter is called the latitude. So the relationship is cos of inclination angle is equal to, so this inclination is the orbital inclination. I will tell. So this inclination is the orbital inclination angle. So that is sine of A into cos of L, where A is the azimuth angle, L is the latitude. Okay, for example, if we take a basic thing, suppose we are launching the satellite from equator. Okay, but the reality is we are not on equator. India is a geographical land which is above the equator. That means we can say the India is located in the northern hemisphere from the equator. So we are above equator. Now suppose assume that we are launching the satellite from equator. Nowadays, people are launching satellite from the sea level. Okay, so different sea carriers are there. So the satellite can be carried through the ships, big ships, which are the carriers, and they will launch the satellite from the sea level. From the sea surface, they will launch the satellite. So that is possible. So here, suppose we are launching from the equator. So equator means we can assume that the latitude of the launching site is 0 degree. So L value is equal to 0. Okay. And what about the azimuth angle? So when the equator, we are launching from the equator, right? So what about the azimuth angle? Azimuth angle should always be calculated from the north. So if you calculate, you know, equator is a horizontal line from east to west direction, and if you see it from the north, then it will be exactly 90 degree. So that is why I have taken the azimuth angle as 90 degree. So what happens here? Sine A is equal to 90 degree, L is equal to 0 degree. So cos of 0 is equal to 1, sine of 90, that is equal to 1. So these two multiplication, it will result as equal to 1. So hence what we got, cos of inclination angle is equal to 1. That means inclination angle is equal to 0 degree. That means what? In this case, the orbit inclination angle is 0 degree. That means what is the orbit? So which orbit we are launching? We are launching to the GEO orbit or geostationary orbit. Okay. So since we are launching into the geostationary orbit, by making or when we launch the satellite from the equator at an azimuth angle of this, then we can launch the satellite to an equator. So this is we can launch the satellite into GEO orbit or geostationary orbit. Okay. So that is why the land-based launch sites are located near equator. So example, Porur, SDSC, and even in our country, we are launching from Sriharikota. Although it is not near, no, it is not exactly on equator, but somehow near to equator. And in our case, in India particularly, if you see the latitude, so latitude of Sriharikota is towards northern hemisphere. So if I don't know the exact latitude value of Sriharikota, but probably it is around 20 degree north somehow. So hence, as this angle, as the value of L will increase, so this factor will decrease, because the cos theta will have a higher value when theta is equal to 0. But as the value of theta increases from 0 degree, that means the cosine of that angle, it will fall. So this value is falling. Look at, have a look on this factor, which is sine of A or sine of azimuthal angle. Okay, so what about the azimuthal angle? Does the azimuthal angle 90 degree at particularly at Sriharikota? Because we are concerned about Sriharikota. Is it 90 degree? No, it cannot be 90 degree. It will be more than 90 degree. Okay, because this is the, let me draw the equatorial line. This one is the 0 degree equatorial line, and Sriharikota is north of equatorial line or 0 degree latitude, and this line represents the uh, longitude, which is from north to south. Okay, so Sriharikota is located from this point. Now you see, if you have a line joining this, so this angle is not 90 degree. This angle is greater than 90 degree. So what happens then? So this will increase. Okay, so this factor, it will balance this equation, that is cos of inclination angle. Okay, so this expression tells that how the inclination angle, that means orbital inclination, is related to the latitude and the azimuth angle. Okay, so at which azimuth angle we want to launch the satellite. Okay, so this GTO inclination depend on the launch site latitude. So to make the inclination angle 0 degree, corrections are applied when satellite is one of the nodes ascending or descending. Semi-major axis and line of nodes must coincide while placing the satellite at GTO. Okay, and for spending minimum fuel, we have to apply corrections. When velocity is minimum, that is at apogee. So you just have a look on this. What we are talking about, this inclination angle. So it is the angle in between the equatorial plane and the orbital plane. Okay, that means you see this plane, equatorial plane. It is nothing but the plane at the 0-degree equator. This particular plane I am talking about. This particular plane. But this particular plane, it represents the orbital plane. Orbital plane means uh, this represents the satellite is not moving on the equatorial line. It is moving in a different orbit, which is having some inclination, which I will draw here. Okay, let me show. This is the Earth, where the satellite is moving like this. It is not moving like this. It is moving at some inclination, where this represents the equatorial plane. Okay, this I'm drawing the 2D diagram. This represents the equatorial plane. This represents the orbital plane. So angle between these two, the angle between the equatorial plane and the orbital plane, that we represent by the inclination angle. Okay. Now, what correction we have to do? Just have a look. So GTO, inclination launch site latitude. To make I is equal to 0, that means while launching, to make the inclination angle equal to 0, we have to make some corrections. So those corrections are applied when satellite is at one of the nodes, whether the satellite is an ascending node or the satellite is at descending node. Okay, do you know what is ascending node and descending node? If I show in the previous one, this is the Earth and the satellite is moving like this. When the satellite is moving from downward to upward, then this is this node, this particular node. Okay, let me use a different color. So when your satellite is rising up, so this particular node is called the ascending node. Now your satellite moves also like this, and when it comes to this node, that means it is falling. So this node is called the descending node. Got the point now? The semi-major axis and line of nodes must coincide while placing the satellite in GEO orbit. So for spending minimum fuel, apply correction when velocity is minimum, that is at apogee. So what correction we have to apply? The correction is, see, this delta V vector. If you see what this line Vs represents, this vector represents, it is the velocity vector along the direction of the orbital plane. Assume the satellite is a GEO satellite. Assume, I'm saying assume the satellite is a GEO satellite and the satellite is moving on the equatorial plane. So what is the direction of the velocity vector? The direction of the velocity vector will be on the equatorial plane. The vector will be directed in on the equator, away from the equator rather, but it will be on the equatorial line. So that is what I have represented. So this plane, which is called the equatorial plane, which I have represented by a black color line. So that is why the velocity vector I have represented by black line with an arrow, which is away from the equator or away from the equatorial plane. So this is what we observed by assuming the satellite rotating in equatorial plane. But in reality, the satellite is not rotating on equatorial plane. Rather, it is rotating at a plane with an angle which is called the inclination angle. All right. So if the satellite is moving at an inclination angle I, so it has the velocity vector. So this particular plane, which I have represented by a yellow color square. So this is the orbital plane, actually where the satellite is rotating. In the previous diagram, you can see here. So this particular plane, this is called the orbital plane. Okay. So if the satellite in practical is rotating on the orbital plane, then its velocity vector will be directed in this direction. So this I have denoted by VA. So VA is the velocity vector of the satellite when the satellite is moving at an inclination angle that is given by A. So this vector is called the velocity vector. Okay. If we have to apply some correction, then we have to make the velocity vector which is aligned to the other velocity vector Bs. That means this VA should align with Bs. So that correction we have to apply. So if you see here the inclination, this inclination angle is the angle in between orbital plane and the equatorial plane. So this is the inclination angle. Now if you see here this velocity vector, it is also aligned on the equatorial plane. This velocity vector, it is aligned on the orbital plane. Hence, the angle in between these two velocity vector can also be called as the inclination angle. It is the same angle which we have represented in between the equatorial plane and the orbital plane. Okay, so the angle I can represent here also is equal to I. Okay. Now, if I make a line joining this point to this point, it will form a triangle. Now, applying the triangle law of vector, I can triangle law of vector addition. I can represent this vector, which is called the resultant vector. This resultant vector is nothing but my velocity change vector or the correction vector. We can rather say. Okay, because what we want this velocity vector to be aligned with Bs. That means other velocity vector. So this is the vector or this is the velocity vector which we call as the correction vector. So we should try to minimize the inclination angle as low as possible. So we have to minimize the inclination angle. So in this, by applying the triangle law of vector addition, we can express the value of delta Vi. Okay, that is equal to Vs square plus Va square minus 2 Va Vs cos of inclination angle, cos of this angle. All right. Now, what is the value of Va at what velocity it is moving in that orbit at an inclination angle? So where the satellite is moving? It is moving in the GSO orbit. Okay. So if we apply the previous formula, that is the third law of Kepler, you will find that means this particular orbit is an elliptical orbit. If you find the velocity, it will come as 1643 meter per second. You see this one. So this one we have calculated for what? Kilometer per second. If you express this in meter per second, it will come 1634 meter per second. Okay, so what this velocity is at what point? This is the velocity of the satellite at what point? Let us move back to the diagram. It is the velocity of the satellite at this point, that is called VA. That means when the satellite is moving in GTO orbit, look at it again, because this formula we have used for elliptical orbit. This formula is for elliptical orbit. Okay, and we have calculated that for at this particular location. So hence the velocity which we obtained 1634 meter per second, this one we are using 1634 meter per second. So that means the satellite, when it is moving in an inclined orbit, the velocity at the point of apogee, it will come as 1634 meter per second. Now this, look at this velocity Vs. What is the Vs? What is the value of Vs? Let us go back. 3.075 kilometer per second. That is equal to 3075 meter per second. So this is the velocity at what point? Can you tell? This velocity is at what point? This velocity at this point, the same point. But the difference is that this velocity 1634, this velocity 1634 is at apogee when the satellite is moving in GTO orbit. Now this velocity 3075, it is the velocity at this point 3075 when the satellite changes its orbit from GTO to GEO. So the velocity increased to this value. And this orbit is an elliptical orbit. This orbit is an circular orbit. So let us do the calculation here. We have used the same velocity over here. Okay, so if you if you are using this value BA and BS in this above equation, so you can put here, here and here. So what will be unknown? So in order to find the change of velocity or the correct velocity correction, you have the value of I, or you should have the value of cos of I. So by referring the previous expression, we know this one, cos of inclination angle is sine of azimuthal angle into cos of latitude. So this is what sine of azimuth angle and cos of latitude. So what is the inclination angle? It is cos inverse of this value. That means if the latitude of launching pad, okay, from which location we are launching the satellite, if that latitude will be given, obviously that latitude will be given. If the azimuthal angle will be given, so what is the azimuthal angle? So when we want the satellite to launch at a certain angle, then what at a certain orbit from the launching pad or from the launching site, then how much is the azimuthal angle the satellite will make from the northward direction? So these two values will be known. So we can find out the inclination angle. So using this inclination angle, we can find out the correction vector, that is del V. Okay. So we should try to minimize this del V vector as low as, means this del V should be as low as possible. That means I can be, then only I will be less. For example, if you see this expression, as I said, I will be less. So cos of I, it will more. When the I value will be less, so cos of I will be more. So when cos of I will be more, so this factor, it will also go higher. So that means this factor minus this factor, since the subtracting factor is coming down, that means this difference it will again reduce, and that will reduce the velocity change or the velocity correction factor. Okay. So now we shall discuss different types of launcher. Some of basic ideas. There are different kind of launchers we have. One is some European countries, they are using a launcher that is called as Ariane, and in India we are using the launcher that is called GSLV, geosynchronous site launch vehicle, geosynchronous launch vehicle. And currently we are means ISRO is working a space shuttle which is reusable, because nowadays whatever the rockets we are using, all the rockets they are for one time use. That means once you have launched the satellite, so all the rockets or the launch vehicle that will not be in use, it will fall down on the sea. Okay, so that is called as a dead mass, that is for no use. But still we are at a very experimental stage for designing the reusable rockets or the space shuttles. And we are using different types of propellants also. One is called the solid propellant. So propellants are the the fuels what the launch vehicle or the rocket is carrying. So this fuel, these are for only to launch the satellite or to put the satellite in the correct orbit. So once that is done, the job of fuels is over. So that they will be detached from the satellite and they will fall on the sea. Okay, so here the launch vehicles mostly are carrying three type of fuels. One is called the solid propellant, another is called the liquid propellant, and the third one is called the cryogenic propellant. So example of solid propellant are the polybutadiene carboxide, oxidizer, oxidizer is some aluminum powder that also can be treated as a solid propellant. And in liquid propellant, we are using hydrazine, we are using oxidizer, we are using also nitrogen tetroxide. And for cryogenic propellant, we are using liquid oxygen and liquid hydrogen. These are for cryogenic propellant. Now, what we have discussed till now, the satellite is launched considering the Earth as a sphere, and there are no impact or there are no effect on the satellite when the satellite is rotating around the Earth. But practicality is something different. Neither the Earth is a pure sphere, nor we can say there is no effect on the satellite. The satellite observes so many effects. Earth gravitational field is on the satellite. Sun's gravitational field is on the satellite. Solar radiation falls on the satellites. And there are many things which affect the satellite. What happens, particularly you might have studied in the school level. That means in a month, the Earth gravitational field also not uniform. It is the gravitational field or the gravitational force is not uniform in the Earth. But particularly in the equator, the Earth gravitational field is less. If you go towards northern poles or southern poles, the Earth gravitational field will be more. Okay, so gravitational field also is not uniform. So the satellite will experience different types of forces, and those forces are not uniform forces, while rotating around the Earth. So let us calculate what those parameters which have the adverse effect on the satellite. So Keplerian orbit parameter assume Earth and satellite as perfect sphere. So what the Kepler has given the laws, he has given by assuming the Earth has a perfect sphere and no longer force acting on them, and there was no other force acting. So in reality, this is not true, and following factors may give erroneous estimation of orbital parameter. So the parameters which gives the erroneous estimation of orbital parameters, they are the non-uniform gravitational field, effect of sun and moon gravitational field, and solar radiation pressure, and finally the atmosphere drag for low Earth orbit. Particularly the low Earth orbit satellites, they are moving at an altitude from the surface of the Earth. It is around 500 kilometers. Okay, so I was disconnected for few seconds. Yeah. So the LEO satellites, they are located at an altitude very close to the surface of the Earth, which is around, around 500 to 1500 kilometers from the surface of the Earth. Now also people are trying to launch satellites at an altitude of 50 and 60 kilometers from the surface of the Earth, which is very close. The airplanes, commercial aeroplanes, they are moving at an altitude of around 11 or 12 or 13 kilometers from the surface of the Earth. So it is just very close to that. That means the effect of the gravitational field is much higher on those satellites. And due to that, whatever calculation, orbital calculation or parameters calculation we are doing for those satellites, so we have to take, we have to consider those effects on the satellite parameters. So this is one effect that is called effect of Earth asymmetry. Equatorial radius is not constant. Earth is not a it's not a complete sphere. You can see it is look like just an apple. At the equator, the Earth is bulged, and towards the poles, north and south pole, the radius is less. So non-spherical shape of the Earth makes the average polar diameter less than the average equatorial diameter. Okay, so if you see the average radius of the Earth towards the equator is 6,378 kilometer, whereas towards the north, the average north or south, the average radius will be 6,356. Okay, probably it will be 22 kilometer less. The radius of the Earth is 22 kilometer less in the northern and southern poles. Another parameter is non-uniform density of the Earth. Okay, so Earth, our Earth is completely consist of 2/3 portion of the um, geographical area is covered by water. 1/3 portion is covered with land. Okay, so the density of density of the Earth is also not uniform. And the gravitational field, if you observe in the towards the equator, the gravitational field is around 9.78 meter per second square. But if you go towards the northern poles, or if you go towards the southern poles, any pole, north or south, you will have higher gravitational field. So which is approximately 9.83. That means uh, around 0.05 meter per second square higher what you observe in the uh, equatorial line. So these lead to non-uniform Earth gravitational field around the Earth. And due to this, force on the satellite varies with its position. Okay, so at different location, the satellite experience different gravitational field because of the non-uniform gravitational field. Okay, then what happens? The movement or the velocity of satellite also changes because of non-uniform gravitational field. So the velocity of the satellite will not be constant. Even if it is moving in a circular orbit, we have assumed in circular orbit the velocity is uniform. But in practice, due to this, the velocity is not uniform. Okay, so we will continue this discussion and the effect of all these factors on the satellites in the coming classes. But if you have any question now, you can ask.